Good evening to all. Welcome to this lecture 2 of this series Introduction to Basic Electronics, and today I am going to discuss about the extrinsic semiconductor materials. And we have two types, N type and P type. So I am going to discuss how these two type of extrinsic semiconductor materials are formed by adding some impurities. And as already mentioned in the previous lecture, that the reference book that I have considered, it is the 7th edition of this electronic devices and circuit theory by Borsted and Nesselstein, right? So just a recap of lecture 1. So in the lecture 1, like I just discussed about the atoms, and then from the atoms we discussed how silicon has some unique property which is not present in the conductor and which is not present in the insulator, and the unique property is due to the presence of 4 valence electrons. And from there we discussed that valence electrons and the shells, the different shells of the electrons, due to that we have the energy levels. And when large number of atoms they are joined in a crystals, when large number of atoms are present in a crystal, so these levels they just convert into the bands. Right? And so instead of energy levels, we have the bands. Why band? Because the electrons that are present in the same shell, they start having different energy, right? And since they have different energy, so instead of having a single value of the energy, they may have a range. The value of the energy of the electrons in a particular shell, they may lie in some range, right? So we have the energy bands. And I told you that the only energy band that we are more interested, it is the outermost shell. So, and that outermost shell, the electrons that are present in the outermost shell, it is known as valence band, right? We also discussed that we have a conduction band, and it is this conduction band, if the electrons are present in the conduction band, then only we may have free electrons, and then only we may have a current, right? So in the conductor, these two bands are overlapped. In the insulator, the gap, which is known as forbidden gap or energy gap, so this gap is too large, so that no electron can jump from valence band to the conduction band. But in semiconductor, this gap is medium level, and by providing some external energy, they may get some some of the electrons can move to the conduction band, and then they can involve themselves in current, right? Thereafter we discussed that the semiconductor material that we considered, it is pure. Intrinsic semiconductor material, they are pure, means we whatever silicon wafer we have, so as per the technology available, we try the purest form of the silicon wafer, so that the impurity may be reduced to 0, or not 0, then whatever the latest technology permits, but ideally we need 0. And why we need 0, that we are going to discuss today. Why ideally impurity free silicon or germanium wafer or the impurity free semiconductor materials are required, and what happen if we add some impurity in the semiconductor material, right? So today I am going to discuss about this extrinsic semiconductor and doping, means what happened when we add some impurities, and by adding the impurities we can form two different type of semiconductors. One is N type, another is known as P type, and thereafter we are going to discuss how the different charge carriers that are generated in these two types, how they flow within the complete crystal or within that semiconductor material, and what are the majority carriers present in the N type as well as in P type, and what are the positive and negative ions present in n-type and p-type. So we are going to diagnose the extrinsic semiconductor material today. So starting with intrinsic semiconductor, like the silicon atoms, since they have this 4 electrons in the outermost shell. So when when two silicon atoms, they are bonded with each other with the help of covalent bonds, right? So when the covalent bonding, due to covalent bonding, the silicon outer shell electrons, they share the electron from the another atom, right? So at the crystal of silicon, it looks somewhat like this, that a single silicon is going to have, it has this 4 electrons on of its own, whereas another 4 electrons will be shared from the neighboring silicon, right? So overall, now with the help of the covalent bond, it got 8 electrons, right? And this we are talking about the intrinsic semiconductor, which does not have any impurity. Now if we add some impurity, like impurity, addition of impurity does not mean that we are going to add large amount of impurity. Impurity means that we are going to add impurity in a very controlled manner, like something 1 impurity in 10 millions, right? In 10 million atoms. So when we add this much amount of impurity, then the band structure, the energy band structure of the semiconductor material is going to change, right? So we are going to discuss what happened to the energy band diagram, right? Now the process of adding the control impurity to the intrinsic semiconductor, it is known as doping. So whenever we add impurity to the semiconductor material, so it means the process is known as doping, and the material that is formed by adding the impurity, it is known as extrinsic material. Now we can have 2 type of extrinsic materials. One is n-type and the another is p-type. So first we are going to look about the n-type. Now in the crystal, in the structure of silicon, right? If in the structure of the silicon, if instead of silicon, if we add impurity such that the impurity element has 5 valence electrons, means it is a pentavalent, means in the outermost shell of this impurity atom, it has 5 electrons, right? For example, like this pentavalent electrons, these 5 valence electrons are present in elements like antimony, arsenic and phosphorus. So if we replace one silicon atom with a phosphorus, as I did over here, so now since phosphorus it has 5 electrons around it in the outermost shell. So when we add this as an impurity to the silicon wafer, to the silicon crystal, then this 3 and this 4, these 4 electrons, they will form a covalent bond similar to the silicon, right? So this and this 4 electrons has formed a covalent bonding with the neighboring silicon atoms. But now we left with 1 electron, and now this electron, it cannot form a covalent bond, but since it is a part of the complete crystal, so this electron it remains free. So this electron is free in the sense that since it is within the crystal, so it is bounded by some energy, but the amount of energy, it will be too negligible that easily by having a very minimum energy, it can simply jump to the conduction band. So the amount of energy that these electrons which are a part of a covalent bonding, So the amount of energy that this electron required, it will be too high in comparison to this free electron. So free electron will, the electron which is not able to form any covalent bonding. So this electron will be free, and this electron will easily be able to go to the conduction band. And we already know that if we have electrons in the conduction band, it means current will flow, right? So over here, when to form n-type extrinsic material, we have seen that simply by adding the 5 valence electron element having a 5 valence electron, we are able to get one free electron for each impurity element. It means if we add 10 impurity element, then how much electrons we will get? We will get 10 free electrons. 10 free electrons, right? And this 10 free electrons will help in conduction of the current, right? So, and this impurity, because this, by adding this impurity is donating one electron which act as a free. So since one electron, so this impurity, it is known as donor atom, right? Because it is donating one electron with the help of which current we can make current may be established, right? So this impurity, it is known as donor atom. Now about the energy band. Now we know that for a simple intrinsic semiconductor, we have, this is conduction band EC, we have this valence band, energy of valence band EV, and this is the forbidden gap or energy gap, right? Now with the introduction, by introducing the impurity in the intrinsic semiconductor, means by forming the n-type extrinsic semiconductor, we just found that for each impurity particle, one free electron is there, right? And this free electron, since it is not associated with any bonding, so it means that this electron need very little energy, right? And due to this, apart from these energy bands, means we have conduction band, we have valence band. So apart from this, we also have another energy level. We have another energy level, and this energy level is known as donor energy level. Why donor? Because it is due to the presence, to the presence of donor impurity atom, right? And this energy atom, like all these free electrons, they will lie on this energy level, and the distance of this from the conduction band, it is just 0.01 to 0.05 electron volt. So it means these electrons which are present over here, this electron, they just need 0.01 to 0.05 electron volt energy, and just by getting this amount of energy, they will simply be able to jump to the conduction band and can establish the current, right? So by adding the pentavalent impurity, another discrete energy level, which is the donor energy level, it is formed within the forbidden gap, and due to this energy level, easily these free electrons can come to the conduction band. And apart from that, not only these free electrons, like suppose if we have some electrons over here, right? And this electron gets some energy. Now this electron, if the electron jumps and just be able to reach over here, at this point. Means this electron, if it is not able to reach conduction band but just able to cross this energy level, donor energy level, then this, while coming down, this electron will just be able to settle at this donor energy level. Means this, by establishing this energy level, donor energy level, this not only supports the free electrons that are available in the impurity, it also supports the electrons that are present in the valence band. Means once they get the energy, they will have two options. One, if they get enough energy to reach this conduction band, they will come directly to the conduction band. But if the energy is little bit less, then they may settle in this discrete level also. So it adds support to the other electrons also, right? So just by adding one impurity, we get this energy level that helps other electrons also to reach to the conduction band. Now, as we mentioned that this free electron is there, right? But and this, we know that electron is negatively, it is negatively charged. Okay, it has negative charge. But since this electron is free and it is extra, right? But this extra does not mean that the atom becomes negative or this complete crystal becomes negative. It does not mean that. Why? Because this extra electron, like this extra electron is there, but with this extra electron we also have extra positive charge within the nucleus of the phosphorus, right? So suppose if we have some intrinsic material and let there are plus 15 positive charges in the as a proton in the nucleus, so 2 electrons will be in the first shell, 8 electrons will be in the second shell, right? And now in the third shell we have 5, right? I just form over here only, right? Now if I remove this electron, then the atom, then if I remove this electron, then the charge that is present, it is 15, but the number of electrons they left, we just left with 14 electron. If one electron is not associated with atom anymore, so it means overall this part, it is positive, right? But this free electron which just come out of the atom, this free electron is also present nearby. Means within the crystal this free electron is also present. Means this atom without this electron, it is positive. But if we talk about a complete crystal, then complete crystal, it consists of this positive plus this one electron. So in all, with this plus this positive, this complete positive plus one electron, means this free electron, it makes our crystal as neutral, right? So even if we have free electrons, it does not mean that our crystal, our material, n-type material, it becomes negative or it becomes positive, right? When this electron is free, then the remaining part of this phosphorus, it becomes positive, and we call it as positive ion, because one electron is detached from this phosphorus atom. So this phosphorus atom, it is known as positive ion, right? But if we look at a complete material, then that complete material, it consists of this positive ion plus this electron, right? So the combination of this electron and this positive ion together, together, it is the material is neutral, right? So it is the reason that n-type material is still electrically neutral, right? It is still electrically neutral. Now coming to the p-type. Now once we know, so overall what we did in n-type, we just add the impurity having 5 valence electrons. Due to the 5th valence electron, we have one free electron available, and this free electron contribute to the current. And this impurity, it is known as donor atom because it uh, it donates one electron, right? And due to this donor impurity, we got the donor energy level, and due to the presence of this energy level, it helps all the electrons, the free electrons as well as the other electrons, to reach to the conduction band. And we also discussed that the n-type, it is electrically neutral. Now same thing we are going to discuss for the p-type. In the p-type, the impurity that we are going to add, it has 3 valence electrons. Now since in silicon we have the 4 valence electrons, right? So when we add impurity like boron, right, so it has only 3 valence electrons. So what about the fourth? Now when we talk about the fourth, so the fourth covalent bond, since the boron does not have any fourth electron, so the fourth covalent bond in this, it creates one vacant position, or we call it as hole, or we can say that this hole means absence of electron. So simply what we can say that when we add impurity having 3 valence electrons, in that case the fourth covalent bond will have 1 electron absent. And as I told you in lecture 1, that the absence of electron, it means positive charge, and we call this positive charge as hole, right? So this vacancy, it is known as hole, and it is assumed to have a positive charge. And remember, as I told you in lecture 1, that this positive charge, it is virtual. As such, it does not have any existence. The existence is over here. When we say positive charge, it means the absence of electron. But how this absence contributes to the current? Now what happened that now this electron, if this electron got some energy, right, and if this electron got some energy, and from here if it jumps over here, if this electron jumps in this hole, then what will happen? Hole will be created at this position, means this hole, it will be shifted over here. So what we can say that this positive charge is shifted, or we can say positive charge has moved. And when we say charge has moved, it means it is a current, it forms a current, right? Because we discussed in lecture 1 that the moment, if the charges are moving, it means current is there, and the charges, it can be positive or negative. So if positive charge is moving, then the direction of the positive charge and the direction of the current will be same. So over here, if this electron shifts to this hole, if this electron fill this hole, then new hole will be created over here, right? And due to this hole, we can say that this positive charge, it has moved from here to here, right? So positive charge is moving. So just by creating one hole, just by creating one absence of electron, we are able to make electrons flow. So this absence also helps in moving the electrons from one covalent bond to another. And if electrons are moving, so it means current is there. But over here, since as such this hole is moving, so when we create the extrinsic material with the help of three valence electron, then the charge carrier, it is the holes. And if we add 10 impurity atoms, it implies then 10 holes will be 10 holes will be there in the complete material, right? So, and if there are 10 holes, means 10 holes will contribute to the current, right? So just by now, because this holes uh, is accepting the electron, means over here this hole, it is accepting the electron from the neighboring covalent bond. So this type of impurity, it is known as acceptor atom. You in for the n type, the impurity is known as donor atom. Why? Because that impurity is donating the electron. Whereas over here, due to three valency in the three electrons in the outer shell, this impurity creates a hole, and this hole, it is accepting the electron from the neighboring covalent bonds. So this type of impurity, it is known as acceptor atoms. Now similar to the n type, due to the presence of this hole, we will have new energy level in between the forbidden gap. So if this is a conduction band, if this is valence band, so due to the presence of this acceptor atom, means due to the presence of this trivalent impurity, one discrete energy level will be formed, and this energy level will be known as acceptor energy level, because it is due to the acceptor atom, right? And again, this energy, the difference between this energy level, the energy, we can also denote it as EA, right? So the difference between this acceptor energy level and the valence band, it is in the range of this 0.01 to 0.05 electron volts, right? And over here, whatever electron, if electrons are over here, so this electron can jump over here, right? And can form the current, right? So similar to the n type, p type also contributes to the current, but in p type the current is formed due to the presence of the holes. And similar to the n type, this complete material of a p type, it is electrically neutral. Why? Because if we just consider the boron now, or if we consider any acceptor atom, let it be plus 13, means in the nucleus we have plus 13 charge, means plus 13 protons, and it means in the first shell it will have 2 electrons, in the second shell it will have 8 electrons, and in the third most it will have 3 electrons, right? Now since this particular boron, if this electron, if it shifts over here, if it comes over here, means over here one extra plus one electron is there, one extra electron is there with the boron, means over here we have one extra electron, right? So the total electrons, it becomes plus 14 electrons, right? Or minus 14, the charge becomes minus 14, right? And since the nucleus it is plus 13, so overall this particular atom, it has negative charge. So if we talk about the individual atom, individual impurity atom, that the individual impurity atom, it will have a positive charge, and we call it as positive ion. Means the impurity atom, it will once it accept, once it it becomes negative in the p type, this becomes positive. So over here, since it is accepting one electron and we have more negative charge, and we have less positive charge, so since we have more negative charge, so this ion, this becomes negative ion. So the acceptor ion, this trivalent impurity, once it accepts the electron from the neighboring electron, it becomes negative ion, right? It becomes negative ion. And but if we look at a overall material, now within this overall material we have this electron present. So even if this electron is lost, if this electron is transferred over here, so still overall we have same number of electrons, we have same number of positive ions. So at the end, similar to the n type, this p type material, it will be electrically neutral. Now the flow, already I have discussed that how we all know how electrons flow, right? And already we have discussed how the holes in the material flow, that simply if we have holes over here, so if this electron, it moves over here, so if it moves over here, or if this is the hole, and if this electrons moves over here, so the hole will be formed over here, means hole has moved over here. Now if this electron moved over here, in that case a hole has moved further. So you can see that how the holes are moving, and since the positive charges are moving, so it means current is there, right? So it is how the holes are moving. Now if we look at the majority and the minority carrier, why? Because if we look at the n type material or the p type material, in both it may have electrons or it may have holes. So both of this n type and p type, they may have both electrons, holes, so both can be there. But if we look at n type, this n type material, in the n type material, the impurity is generating, it is donating the electron, and so since the number of, since the addition of electrons are there with the in the n type material, so it means there will be more electrons, so the majority carrier in the n type will be the electrons. So since n type material has like the impurity has donated the electron, so electron will be the majority carrier, whereas holes will be the minority carrier. Now remember, due to the energy, even if there are, like, if we have this type of bonding, right, and we have this electrons over here, so even if it is not replaced, like even if this silicon is not replaced with any impurity, still this electron may move out of the covalent bond, and due to the energy that it gained from the external energy. So if somehow, if this electron got the energy, this electron will get free, and this, if it get free, then it means hole will be created over here, and means due to the energy, external energy, we may have holes as well as electrons in the intrinsic material also, right? So in the n type, we will not have only the electrons, we may also have the holes. But since apart from the number of electrons and holes that are present in intrinsic, in pure semiconductor, by adding the impurity, we increase the number of electrons. So the majority carrier in the n type, it will be electrons, whereas minority carrier will be hole. Minority carrier means the current due to hole, it will be very less, very negligible, whereas the current due to electrons in n type, it will be significant. And similarly, opposite will be for the p type. In the p type, since due to the presence of the impurity, we created the holes, right? Whereas in intrinsic, we have equal number of electrons and holes. So but by adding the impurity, the number of holes has increased. So in p type, we have more number of holes, whereas less number of electrons. So it means that the current in p type, the current will be mainly due to the holes. So holes will be the majority carrier, whereas electrons will be the minority carrier. Means very negligible current will be there due to the presence of electrons in p type, right? And now, since, as we already discussed, that since the impurity atom has donated its electron, so it acquires a positive charge and it is known as positive ion, right? And apart from that, this n type, majority of the carrier, charge carrier, it will be electrons. So these are the electrons, and some holes may also be there. So these are the holes. It means n-type material may have positive ions, holes, and electrons, and the number of electrons will be very large due to, and it is the main charge carriers, majority charge carrier in n-type. Whereas in p type, we have the, sorry, it is negative, ions. So in p type, we have negative ions, we have holes, we have electrons, but the number of holes, they will be very large in comparison to the number of electrons, right? So the summary of whatever we have discussed is listed over here. So in n type, we have pentavalent impurity, whereas in p type, we have trivalent impurity added. N type impurity is known as donor atom, p type it is known as acceptor. The energy, discrete energy level is formed, and this discrete energy level in n type, it is just below the conduction band, whereas in p type, it is just above the valence band. And the majority carrier in n type, it is electrons, in p type it is holes, and the type of ions, this impurity atom, it will, n type, the impurity atom, they will be converted into positive ions, and in p type, the impurity atom will be converted into negative ions. And last, now at room temperature, we know that at room temperature, in an intrinsic material, there is about just one free electron for every 10 raised to the power 12 silicon atoms. So it means if we have 10 raised to the power 10 silicon atoms present, then only one free electrons are there. Whereas for every 10 raised to the power 9 atoms, germanium atoms, we have one free electron, right? Now, if we add just one impurity in 10 millions, means one impurity in every 10 power 7 atoms of the semiconductor, means 10 power 7 atoms of silicon or germanium, then what happened? If we look at the silicon, if we add one impurity, then just by adding one impurity in the silicon, we will be able to generate 10,000 charge carriers, right? So a crystal having this much atom, and due to this much atom, we just have one free electrons, means negligible, right? So just by adding one impurity to 10 power in every 10 power 7 atoms, so we will be able to have 10,000 charge carriers. And you can imagine how much concentration of carriers has increased. It has increased from 1, it has increased to, it has increased to 1 lakh. It is not 10,000, it is 1 lakh, because just it is 10 power, it is 10 power 5, so it is 10,000. No, 1 lakh, it is 1 lakh. So you can imagine, just by adding one impurity we are able to have 1 lakh charge carriers, and this 1 lakh charge carrier will then contribute to the current. So it is the reason that our intrinsic semiconductor, it should be as pure as possible, because the impurity, we by adding the controlled impurity, we can increase the conductivity of the semiconductor in a controlled manner, right? So yes, this is so if you have any doubt, you can put it in a comment box. So, and don't forget to like this video and subscribe my channel. If you have any doubt, you can post your questions on the comment box later also. So uh, so I guess there are no questions. So thank you everyone for patiently listening in. Thank you.